Hello and welcome to the series of RapidMiner videos. My name is Dr. Marcus Hoffman and I'm a lecturer at the Institute of Technology Blanchardstown and also the principal investigator of this project funded by the Irish National Digital Learning Repository. The series of RapidMiner videos was created in close collaboration with Ralph Klinkenberg and Dr. Ingo Merswa, the two founding members of RapidMiner. More videos as well as additional material to some videos can be found at www.rapidminerresources.com. I would now like to introduce Ralph Klinkenberg, who will talk you through this tutorial.
Welcome to RapidMiner. This video is about learning decision trees from data. So let's first take a look at some dataset and then let's generate a decision tree from this dataset. Let's start simple using the iris dataset. When looking at the data, see that we have 4 numerical attributes, all real valued, and a nominal label. It's a classical setup for a decision tree. And we can just go back, add the modeling technique for classification, and under decision trees or tree induction, we find a decision tree. So this is the standard decision tree without any change in parameters, and this is a resulting decision tree. A decision tree is like a tree upside down, that is, the root is on the top and the leaves are at the bottom. And the idea is that when a new instance needs to be classified, you start with a root node, perform the attribute check, in that case check the size of A3. If A3 is smaller or equal to 24.5, the new case can be classified as iris setosa, like 50 cases in the training set. This bar is all blue, that means it's a pure color, pure class, no other classes in the training case distribution for that branch. In the case that A3 is a measurement above 24.5, another test becomes necessary. If A3 is very large, that is above 5.15, then the classification will be iris virginica. In the training case, 34 cases fell into that branch. In the medium range, when A3 is greater than 24.5 but smaller than 5.15, another test needs to be performed on A4. And for the large cases, again, it can be classified as iris virginica, and in the medium range, it's mainly the green case is the iris vesicular, and the width of the bar indicates how many cases are covered in the training, and the distribution of the colors indicates the class distribution. In that case, 50 cases of vesicular, which is green, and 8 cases of virginica, which is red. So this tree has been automatically generated from the iris dataset using the default parameter setting. So what could we change about the parameters? When building the tree, the learner has to decide which attribute to put to the top, which is the most helpful attribute for classifying the instances. And the criterion for selecting the best attribute can be selected. Standard is gain ratio, but alternatives are information gain, Gini index, or accuracy. Depending on the size of the tree, sometimes somebody wants the system to have more generic trees that generalize stronger, so one can increase the minimal size for a split. That is, if there is fewer than, for example, 4 cases, there will be no more split into finer grained leaves. Similarly, the minimal leaf size can be defined. Sometimes it's important to not grow the tree if there's no significant gain, and therefore there's a parameter called minimal gain. So the tree is only grown if there is a certain gain in the criterion. So if gain ratio doesn't improve by at least 10%, there's no additional layer in the tree. If you have a dataset where the tree doesn't grow as much as you would like, it's a good idea to decrease the minimal gain to allow a better tree growth. Similarly, if the tree grows too much and the leaves are not representative, not generic enough, then you may want to increase the minimal gain. Humans are one of the addressees for decision trees. The trees are decision mechanisms that you can automate, but they are also human readable. But humans can't read arbitrarily complex trees, so you can limit the depth of the tree. 10 to 20 should be a reasonable number. I don't think any human would be able to really understand a tree with more than 20 levels and an accordingly wide width. Looking at the confidence level, This is something relevant for pruning especially. And what's pruning? Well, sometimes a tree grows too much and is overly specific on the leaves. Then you can go and cut it back. That's what's called pruning. And you can do the pruning either after growing the tree or already while you're growing the tree. And this is called pruning and pre-pruning. The standard is that it's turned on, but you can also turn it off, which might be a good thing to do if the tree doesn't grow as much as you would like it to grow. These are the major options that you have when growing a tree. Here it worked quite well, so for this data set we don't want to care too much. Let's just check another data set. So let's use the decision tree with the default parameters and see what happens. As you can see, the tree is a little bit larger, but it's not really a surprise because the data set is larger. There are 16 numeric attributes, and the problem is a bit more complicated. It's to distinguish mines and rocks in a naval environment based on sensor measurements of 60 sensors. So it's 60 numeric attributes for a two-class classification problem, and you can see the tree is still reasonably sized and you can still read it. So first check would be on attribute 11, next checks on 45 and 1 depending on where you branch. 10, 11 is similar range. And what could you do to change this kind of a tree? Well, one thing you could do is to discretize the data, go from numeric to nominal. For example, you could discretize the value ranges into 2 or 3 bins for each attribute and see if that has an impact on the tree. Now the tree became much larger, but was it good or was it bad? How would you want to judge, except maybe for design preference if you prefer smaller or larger trees or narrow or wide trees? Well, to decide what is better with or without discretization, you could use a cross-validation setup. So let's add a building block. So let's remove the decision tree and replace it by a cross-validation. Let's take a look at the performance. Let's first do so without the discretization. The accuracy is 67.8%. And while the majority of the cases is classified correctly, there is still a very large number of error cases. So now let's do the same with discretization. Before we do it, just remember 67.8% accuracy, and now with discretization we have 75.45. That's about 7% more. That means by re-representing the data from numeric to discrete classes or intervals, we actually help the decision tree to better learn the model on the data. So one way of changing parameters would be to change the decision tree parameters that were specified, like criterion to select or criteria to increase or decrease the tree growth. But another option to modify the decision tree performance is to work on the pre-processing side, especially to try discretization. Thank you very much for your attention.
For further information on RapidMiner, please go to www.rapidminerresources.com or www.rapid-i.com. If you are interested in upskilling, please go to www.itb.ie, where you will find more information about our distance learning MSc in computing science, in business intelligence and data mining. Many thanks to the Irish National Digital Learning Repository for funding this video.